Okay, so let's do our third topic. So after this, like I said, we'll move on and we'll actually do some more tasks. If I can be actually really honest, we actually aren't even doing energy yet, to be fair. I'm putting this in the energy unit, but these first three topics are really intro topics. We have to talk about how to measure values. We have to talk about how to put them into formulas. After that, we have to talk about the need for being able to graph your data and the reason why that's valuable in the sciences. And then after that, then we'll actually start talking about energy some more. Does that make sense, though? So, like, I threw this into the energy unit, but, like, really this is intro stuff. So if you're comparing to, say, like, what Ray's class is doing, you know, like, we're doing intro stuff still, too. So anyways, when it comes to graphing, here are the 4 things that I've got as the to understand goals for the day. So we'll read them off one at a time here. Number 1, I want to talk about requirements in order to create a proper graph to use for analysis. Like, what should a good quality graph have, right? We'll get to that. These next ones, they kind of just all blur together. We're going to talk about how to calculate the slope of a graph and how it can be helpful in solving physics equations. We're going to talk about how to calculate the slope of graphs that are not linear. We're going to talk about how to calculate areas under graphs. It's all going to kind of flow together, ideally, different circumstances. So let's start with the first one, though. I'm hoping that over the next few slides, I'm going to be able to impress upon you the need for, like, graphs are valuable in the sciences, right? Like, sometimes we get a little annoyed at having to plot them by hand, and I'm going to show you how to use graphing calculators, by the way, to save you a ton of time. Because if you have a graphing calculator, you can make a pretty awesome graph in about, like, a minute and a half. Otherwise, it takes you a while to plot it, but, like, graphs have value, okay? It gives you the ability to see your data. You can actually calculate a lot of things based on a graph. So I found this slide online that I think is creating a winning graph. These are some of the things that you're going to want to make sure your graph looks nice, right? So number 1, you should probably have a title, especially if you have multiple graphs going. Because, I mean, not that we're to that point yet, but at some point if you go off in the physics or chemistry or bio world and you're collecting your own data, you're doing an experiment, you'll probably have multiple graphs, right? To represent the work you did. So put a title on it if you can. You definitely need labels. This one is a must-have. You must label the 2 axes. If I use the word x and y axes, is that something you're all familiar with, that word, those words? Right. So your x and y axes have to be labeled with units. You know how a second ago we were talking about measuring things in centimeters per minute? Right? Like, if you're putting something on the y-axis and something on the x-axis, make sure you label what unit you're measuring it in, because that can matter. You have to make sure you're clear about your scale. So that's like, as you put little notch markings on the side, make sure you're consistent. This is 0, 2, 4, 6, 8, 10. And make sure it's consistent. You can't go 0 to 2 and then go up to 5 and then go up to 22. Like, it has to be uniform, I guess. I think most of you get this intuitively. And if you need to, you might need to have some sort of key if you have more than one data getting plotted. Okay, so check. That's our first topic. That's the basics of a graph. Let's talk about why you'd care about a graph. Oh, no, hang on. One more thought before we get to that. Do you guys know these words dependent and independent variables? If you haven't, the dependent variable, this is crazy that we chose this word, but the dependent variable depends on the independent variable. And it makes a difference for how we conventionally draw graphs. We always put the independent variable on the x-axis, and we put whatever depends on it on this axis right here. And I like this picture because I think it helps illustrate it. Here they plotted the number of cars and how much money you made. If you were to talk through which one depends on the other, the amount of money you make depends on how many cars show up at your car wash. Is that fairly obvious? More cars don't necessarily show up at your car wash if you make more money. Now, granted, if you're popular and successful, then maybe more cars might show up, but that's not really the relationship we're looking for. You see the difference there? Here, if more cars come, you'll make more money. And this one right here, the other way of putting it says, if you make a lot of money, will more cars show up? Maybe, but I'm not sure that that's the relationship we mean, right? So, okay. Has everybody heard of the phrase y equals mx plus b from like a math class at some point? It's basically your very generic way of writing the slope of a graph. One of the reasons why you might want to graph data is because if your data is linear, which means it has a nice slope to it, you can draw what's called a line of best fit. And that line of best fit kind of allows you to show and demonstrate trends. And so I found a couple of graphs online here where people plotted some data, right? And you can see that right here, 2 went with 1, 3 went with 2, 5 went with 4, 6 went with 5. And I'm starting to see a very, very clear relationship. But what's cool about showing it in a graphical format when you collect your data is, can you see how this point right here was an outlier? Something went wrong when measuring your data. And that's why we talked about this on our day one, is that this data point is probably not accurate. That makes sense? Precision is the degree to which you recorded your value, but accuracy, was it done correctly? And based on this data, I think that 1 giving 2, 2 giving 3, 4 giving 5, and 5 giving 6 makes a whole lot of sense, but this one seems to be off the chart a little bit. And that happens. In science, nothing is ever perfect. There is always some sort of experimental error. Someone screws up. As an example, on Monday we're going to race Hot Wheels down the track. Once in a while, a Hot Wheels car leaps the track and falls off. It happens, right? It means that we have a data point that's an outlier. We record it, we recognize it, and we then try to figure out how to deal with it. Classic example I might give you is, say you're a biology researcher and you've made a new drug that cures cancer. Cool. And you ran clinical trials. And in clinical trial 1, it worked. In clinical trial 2, it worked. In clinical trial 3, it worked. But in clinical trial 4, it didn't work. But in every other clinical trial, it worked. You have one outlier. Now, this is where ethic in science comes in, but does that mean it's okay? To what degree would one outlying data point be considered allowed? Because maybe the one clinical trial that didn't work, we didn't realize it, but the reason why the medication didn't work is that particular person had bananas for breakfast that day, and we didn't realize it, but bananas counteract the medication. Do you see how I can come up with some sort of ridiculous theory there? But we might not have realized if there was one outlying data point. How many outlying data points would it require before you decide to go, oh, this study doesn't count anymore? There's no right answer to that. Ethics in science is a huge conundrum as to at what point are you okay with the data. Take this one right here. This is the flood data for the Embarrass River near Embarrass, Wisconsin, I guess. And I mean, I don't care what the data is, right? But you'll notice that I found a trend, hey? There is a trend that seems to suggest that this data is fairly linear. And this data point over here seems to fit that as well. But I've got a few data points that don't fit anymore. This data point right here is definitely a little out there. For what reason, I don't know. Whatever it is that they're measuring, for whatever reason on one day it just didn't fit. And maybe these 2 data points right here didn't fit as well. But if we're okay with throwing out a little bit of our data, or at least weighing it appropriately, then we can use this still. Okay. When we give you word problems, we tell you that the velocity was 35, the time was 15.2. That's not physics, people. You can't run a trial once and use that data. Does that make sense? That is just not acceptable in science. We would need to average many trials together, collect data points over time, and say, okay, we have a lot of data we've collected, right? You guys understand that? That would be very bad science. I have discovered that when I do this thing once, this happens. Therefore, this is my law. Right? Imagine that I came up with the law of gravitation after looking at a helium balloon once. I let go of this object and the helium balloon rose. Therefore, gravity isn't real. No, that's one data point. And we need to research more as to why that occurred, right? Anyways, I think I'm making my point well enough. Here is a great example about how people try to use data. Did I talk about big data when we talked about our grades conundrum and how people try to collect data so much because they think that more data is helpful? And it kind of is. Here's a great example that I like. This is hockey. And what this particular person did is he plotted hockey players. This is how many points per game they had in the OHL. That was when they were minor hockey, like Hurricanes level players, right? And then they plotted it versus how many points per game they had in the NHL. And they wanted to see whether there was a correlation between players who were good at the minor level and the professional level. And what you'll notice is that there's kind of a trend. Right? look right here. Here's a whole bunch of players who actually had no points per game in the NHL, but they actually had points in the OHL because they never made the NHL. You can see how that's not the y-axis works here. They had points in the OHL, but they never made the pros. And here's somebody over here that had 1 point per game and 0.5 basically. Right? And so would you say that there is a strong correlation here? I don't know. It's pretty scattered, isn't it? Right? Like this is not strong. In fact, there are actual statistical measures. One of them is known as an R-squared value. And an R-squared value is a way of trying to determine how close this line is to linear. If it is 100% perfectly linear, the R-squared value is 1. And so you guys can see right here the R-squared value is 0.45, which means there's not really a great correlation, actually. There are some players who sucked at the OHL who are great hockey players. And there were players who were great in the OHL who weren't good professional hockey players. Right? If I were to go back to the data right here, I would suggest that this data right here would have an R-squared value of like maybe 0.9. It's much closer to 1. And this data right here is also really good. In fact, if I could actually eliminate this one outlier, this data would be exactly an R-squared value of 1. Does that make sense? Because like it would be exactly linear. You guys can see how the line of best fit, though. They didn't draw it through these points. They dragged it down a little bit to account for the outlier. Here's another one, and sports is another great example that people have when they're trying to figure out making predictive models. This is about something called WAR. Baseball, it's about wins above replacement. Okay, now don't worry too much about the fact. Wins above replacement is the way that baseball analysts try to figure out how good a player is by figuring out how much this player would have the ability to influence the ability to win if you just pulled a random person in off the street. So like if a random minor league baseball player were to take your place, you are this much better than them, and we manifest that in how many times a team wins. It's a metric they use to try to figure out how good a player is. Is that good enough for now? Now what they've done here is they've plotted the average wins above replacement for a player based on their age. And what they've noticed is that players peak at about 29. Can you see that? Right? Like this is a rookie at 23 or 24. They're okay. And then as they gain experience in the league, players get better. And so based on this data, the average baseball player, it peaks around the age of 27, 28, 29, 30. Right? And then maybe this makes intuitive sense, but as players get older, they're not as good anymore, right? No. Unless you're Tom Brady. Most players in your late 30s and 40s are not still superstars, right? And eventually they retire, and the trend goes down, right? Do you see how this is valuable for certain disciplines? Now, this isn't even science. This is people trying to take science and apply it to sports, right? But that's the point I want to make, is that there is value in being able to plot data. So what I want to do now is I want to run us through an experiment where, let's say that this was data we collected. This is an experiment where, for example, you recorded the distance that something traveled, and at that marker you found the speed of the object. So this could be like, say, a police officer who is standing there with a radar gun, and he recorded the distance the object traveled. The radar gun tells him the speed at that moment, and we've recorded 5 data points. The question now is, what can we do with this data? Okay. Now, ultimately, our goal is going to be to calculate the acceleration of this data. So to kind of illustrate how this would look, here's the information we have. We have acceleration is something that we would like to solve for. We have multiple data points for velocity final. So if it's okay, can I just write like a line underneath here? We have velocity final. We actually have it 5 times. We also know the total distance traveled. That has been given to us as well. And it was sneaky, but it said that, actually I didn't even say as much here. The object started at rest. I should have mentioned that. I kind of screwed that one up. The object, let's have it start, not time being 0. What are you doing, Chris? Velocity initial. Let's make the object start at rest. So far, so good? So now what we're looking to do is try to figure out how to solve for acceleration. Well, one option would be to take the formula so let's find a formula. What formula involves A, VF, D, and VI? And it's the formula VF squared equals VI squared plus 2AD, right? There's your formula. That's why we learned it yesterday. And we need to algebraically isolate for A. Okay, so how do we algebraically isolate for A? Well, wasn't VI 0? Didn't I tell you that we're starting at rest to make it simple? Can I just cross that out then? Is that cool? So it's actually pretty easy. How do you solve for A? Divide both sides by 2 and D. Divide this side by 2 and D. I now have my formula. Acceleration is whatever velocity final squared is, divided by 2 times distance. Well, you could then solve for acceleration a few different ways. Option 1, you could take this velocity final, square it, divided by double the distance, and that would give you acceleration. In one case. You could then do it again and again. Can you see why I now think it's better for you to do your algebra first? Because if you do all your algebra first, all you have to do now is plug in your velocity final of, say, 12.5, divide by 2 times 15.6, and you've got A1, let's call it. But if you've already got your formula ready to go, A2 will be, where is it here, 13.5 squared over 18.2 times 2. Do you see how I'm saving myself some time by pre-algebraing this? Right? And then I can plot in data. Now, I'm actually not even suggesting that's the best method of solving, though, because I don't know if one of these data points is out of sync. If I graph the data, I might be able to see if we have outliers. Because can you guys look at this data in a chart and tell me which one of these data points something went wrong on? Because I'm going to tell you, one of these data points, something didn't work right on. One of our data points was not correctly measured. So by graphing it, this makes a lot more sense. And here's what we're going to do. We're going to graph this part right here. You guys heard of slope before? You know how slope is rise over run? I'm going to make the rise of my graph VF squared. I'm going to make the run of my graph be 2D. And since rise over run is slope, if I find the slope of my graph, that'll be the acceleration. Isn't that kind of cool? So we're going to show you how to do this on a graphing calculator, because doing it by hand kind of sucks, let's be honest. No one likes graphing by hand. We have computers, let's use them. But for our first example, if it's cool by you guys, can we just graph this one once by hand? And I'll even do it for you here. So I've got a sheet of graph paper as my next slide. So the first thing I'm going to do is I'm going to try to create a nice little graph going on here. So I'm going to put an XY axis here. And this may be the only time we really graph by hand, because after this it's redundant. What did we say our rise needed to be? I think it was VF squared. Okay, so on this axis, I'm not actually going to plot VF, I'm going to plot VF squared. And on this axis down here, our run needed to be 2D. And the reason we needed that is because we made an equation where acceleration was VF squared over 2D. So if we can plot this graph, VF squared, the slope of the graph is then my acceleration. But better yet, when I plot all this data, if there is an outlier, I will see it. Fair enough? Okay. So the downside to this, though, is I need to remake my data, though. So I need to go back in the table here, and I need to make a brand new data table to plot, because the original data that I have isn't actually in the right format yet. I can't even put my axis labels on yet, because I don't even know how big some of these numbers are. So there is a bit of tediousness to making a graph. However, there is huge value in making graphs if you're willing to take the time to do it. So step one, first I'm going to make a new table of values, which is going to be VF squared and 2D. So bear with me. I'm going to start squaring all those velocities. 12.5 squared is 156.25. 13.5 squared is 182.25. Everybody get what I'm doing here? 231.04. 262.44. And 295.84. Everybody cool with that? And then in order to make my equation be valid, I have to double all my distances. I could probably do it in my head, but let's not make a mistake. So this one is 31.2. 36.4. Get rid of that. I should use it. 40.4. That's like 52.2. Yeah, that one I do. I want to do a 7.2. 59. Everybody good with that? Okay, next step. Now we should then plot our data on a graph. And we need to make some active labels. I'm going to suggest, though, that we don't actually have to start at 0. Okay, you don't have to make every graph start at 0. I think I'm going to make my, remember how this is my rise? This is my run. I'm going to make my graph go, say, from 30 up to 60. See how that would cover all my data? That'd be reasonable. And in this dimension right here, why don't I go from 150 up to 300? See how that would work there? So, in my y-axis, I'm going to make this be 150. And this is where it takes a little bit of, like, finessing to make it work. If I made it 150, I made that, say, 175. I'm just thinking out loud. Would that make it 200, 225, 250, 275, 300? It's not bad. I know I'm not using all of my graph area, but is that reasonable enough? I mean, it's a big graph because I'm using the smartboard, right? So I know that that's a little bit, can you write nicer than me? But is that good for now? And then on the other axis, on my x-axis, 30 to 60. So if I make this 30, then maybe I can make 30, 35, 40, 40, 45, 50, 60. Everybody cool with that? Now start plotting. Because like I said, when I designed this problem, I made one of them be an outlier. Now it really depends on how you stretch your graph as to how much it'll look like an outlier. So I'm hoping this will work. Let's plot it. I have a data point that should be at 31 and 156, let's call it. So 31 would be like right about here. And 156, let's call that somewhere about there. And then we need a data point that's at 36 and 182. So 36 would be about here, 182 would go about there, give or take. Next data point is at 2, it's at 40. Then I have a data point that's 2 and 260. 52, 260. 260. Hang on. Okay, 50, that'll be 52 and a half. 52 would be there. What did I say, 262? I think it's there. And then for the last one, 59.4. Let's call that 60, basically, and 295. Pardon me. 60 is right there. 295 would hit about there. Which data point is an outlier? I'm going to use a line tool to try to draw a straight line through all these. If I were to draw a line of best fit, I feel like that's not bad, eh? You see that? But one of those data points I'm not in love with. Data point number 3 seems to be a little bit off kilter for whatever reason, right? The word we use to describe that? Accuracy. Right? And I mean, humans are fallible. We make mistakes, right? Nothing we do is going to be 100% perfect. And so when this data was being recorded, something happened. I don't know what it was because I didn't do the experiment, but do you see how this was valuable though? Now, if, for example, you'd have said, Chris, I can just take this data right here and average it, that would be dangerous. Because one of these data points, this one right here, I think the third one, wasn't a really good data point to use, right? So if you'd have said, Chris, I'll just add all of these up and divide by 5, I'll add all these up and divide by 5, you've now included in your data set a point that I don't think we should have. Make sense? Do you see where there's value in graphing now? Right? And you could go 15.6 squared divided by 12.5 times 2, get an acceleration. You could do this 5 times over, but I think this gives a great visual. Okay? So now here's the last step. All we got to do is do a rise over run. If we find the slope of this graph, I'm much more confident in the accuracy of that. So what I'm going to do is I'm going to make like a triangle from there to maybe here. So I made a triangle out of this right here. And then I'll record the rise over run that I've got. So based on this, I think my rise here goes from 200 to 275. So let's call that a rise of 75. Everybody good with that? This was 275. This was 200. So the rise is 75. And then from here, I think I started at 40 and I finished at 55. So from 40 to 55 is 15. So my rise was 75. My run was 15. I've got an acceleration that I believe is about 5. And, I mean, this is where there's that wiggle room. The precision to which I record this, maybe I'm cool with 5.0. I don't know. What do you guys think? Should we make it 5 point something? Or do you not feel like we can guarantee? Like, do you think it's 5.1? Do you think it's 5.2? Do you think it's 4.9? I don't know. Yeah, and so for me, I might only feel confident in saying 5. Maybe one significant digit. That's what I can guarantee, right? Now, here's the thing you could do. You could go back and take this data here. Remember the data that we plotted? I could look at all these points again. I could take this and divide by this. So I'm going to try it. 156.25 divided by 31.2 gave me a 5.008. Okay, cool. And when I took 182.25 and I divided by 36.4, it gave me 5.0068. All right. When I took 231.04 and I divided by 40.4, it gave me 5.71. But that, I kind of knew that, right? Wasn't that my outlier? When I take 262.44 and I divide by 52.2, I get 5.027. And when I take 295.84 divided by 59.4, I got 4.898. What can I say with confidence? To be honest, I could say 5. I think I might have even been able to say 5.0. I'm not counting this point, right? We knew that that one was not being counted. This is 5.0. This is 5.0. This is 5.0. This one would round up to 5.0. So, but this is where you need to choose what the most appropriate precision is. Precision and accuracy are inextricably linked. Precision is what you choose to measure to based on what you feel like you can accurately say. So I think if this were me, I would have said that 5.0 meters per second squared is probably what I feel comfortable with, but I'm not comfortable with saying anything more than that because, I mean, I had a 4.98. So. That was the culmination of 3 days to get you to that point right there. Right? Do you kind of see why I went through all the stuff I talked about for accuracy and precision, then for formulas, and then to get to this? Because this is what science is. Right? And I'm going to give you a worksheet, but I need you to know that I don't believe that that's physics. This was physics, right? So we'll do a lab on this as well. But yeah, this is cool. Hopefully, like, you enjoy that because, like, that's actual application. It's not just solving word problems. So, all right. I'm going to move on if that's okay. Any questions on that? So, question 2 then. Do you feel like you understand how to calculate the slope of a graph and how you can use it to relate it to a physics equation in order to solve a puzzle? Now, when we're talking about graphs, there are many typical graphs. I gave you a graph of VF squared divided by 2D, but there's some other graphs that you probably are familiar with. These are position and velocity time graphs. And another thing that a graph is good for is that it can tell a story. It can tell you what's happening in a particular scenario. For example, in this particular position time graph, I can tell you that you're going the same speed. Because it's a nice linear straight line, I know that position, which is d, and time, which is t, that's equivalent to velocity. Because we have a nice consistent slope, my rise of d, my run of t, gives me a slope. Since my slope is nice and consistent here, it looks like we're going the same speed the whole time. That makes sense. Or on this graph right here, I can tell you that this is a graph where the rise is velocity, the run is time. Hey gang, what's velocity over time measure? What's v over t? Acceleration. Acceleration is v over t. Which means that if you have a slope of a graph right here, here's an uphill slope. You're speeding up. Here's a negative downhill slope. You're slowing down. And what's the slope when the graph is flat? 0. Well, that means you have no acceleration, which means you're on cruise control, right? This is the story of a van speeding up, hitting cruise control, and then braking, basically, right? You can use those same principles to, interpret data, right? So here's a couple more to kind of illustrate it. Here's a velocity time graph. Yeah. Here's a velocity time graph of someone camping. Flat line across the plot. What is your speed? Nothing, dude. I'm sitting in my chair in front of a fire, right? So this is a flat line graph, right? Here is a velocity time graph of you canoeing while you're gone camping, right? And so the line is straight. Let's talk about that again. The rise was velocity. The run was time. If you do velocity over time, isn't the slope of that acceleration? Well, the slope of this graph is 0 because you're not accelerating. They're moving, but they're just going the same speed, right? This is just a nice leisurely canoe ride. Take this same one right here. Here's velocity time again. Your rise is velocity. Your run is time. Rise over run. Slope of this graph is acceleration. See how the acceleration is going up? But that makes sense. These sprinters are accelerating. They started with no speed, and they got to get up to top speed right away, right? So once you get these principles of how to use a graph like that, they're very helpful. So let's talk through this graph right here. What is the story of this graph? First note, this is a velocity time graph. So if you have a velocity time graph, the slope of the graph is acceleration. So this is negative acceleration. Going backwards. This might be a person backing out of a parking lot. Because that means that their velocity is now negative 4 meters per second. They're going in a backwards direction, right? And then they go on the same speed for a little while. So this is you accelerating backwards, then you're still actually traveling backwards, and then you speed up a little bit more backwards, right? Because your velocity is going backwards. And then all of a sudden it changes right here. All of a sudden right here, there's actually two things happening. From here to here, you're actually braking. This is actually the brakes, because you're going from negative 6 meters per second to 0, which means you were going in reverse, and in reverse you hit the brakes. And then at this point right here, you started going forwards. Now, this might be better described as Vin Diesel in Fast and Furious, like driving backwards in his car and then doing one of those cool e-brake moves and spinning around the other direction. That might be a better illustration for how quickly this happened. But yeah, this was going backwards to going forwards, and now you're going the same speed forwards. Okay? And that's one of the things I want you to be able to do, is to interpret a graph. So here's another one. Here's a position time of a dragster. Now, what you'll notice about position time is position is about your distance. Time is about time. Velocity is distance over time. The slope of this graph is your velocity. However, does this graph have a consistent slope to it? The slope is actually getting faster and faster and faster, which is now getting to our third topic. What if we need to find a slope of a graph that's not linear? This is not linear. This is speeding up. This is actually accelerating. You were going that speed. Now you're going this speed. Now you're going this speed. Every time a new second happens, like your velocity is getting faster. You're accelerating. So our next question is, how can we talk about that? Here's a slide that just kind of reiterates what we talked about. Graphs are linear, right? Many graphs are linear. So they have slopes. And I can't give you a hard and fast rule of how the slope works, but the slope of a graph typically has a 4 feet. If I give you a graph and there's a slope, all you got to do is figure out, well, what is your rise? What is your run? And what is rise over run? divided by time equals velocity. Look at this graph. Which car is traveling faster? Which of these colored cars here is traveling faster? Blue. Blue is traveling faster. Why? Because it's a steeper slope. If it has a steeper slope, it has a steeper velocity. Why? Well, velocity was yellow car started catch up right there. The yellow car started right away. The blue car waited for 5 seconds. And then 5 seconds later hit the gap. The blue car caught up, and right here is where red and blue car. And if you haven't done math, don't worry, you'll learn it. I mean, can you see the overlap between how math and physics are so interesting? Exactly, that's a great way of putting it. Physics is math with you in it. And you need to have some equation, right? Like, that's a big equation sheet. But yeah, and that's what I love about physics, though, is that you should go do stuff, right? You know, like, let's go, race cars down the track, or, you get to make experiments. So I want to do lots of labs. Okay, let's talk about those non-linear graphs, because not every graph is straight lined. Okay, for example, let's say that I gave you this position time graph, and let's say that I gave you the curvy graph. It by its very nature means that the velocity is changing. It has to be. If the velocity was constant, it would have been a nice straight line. So here's how we solve this puzzle. We find what's known as an instantaneous velocity. Light's bouncing into my eyes. I'm just going to move to a new spot. Sorry. It's like bouncing right into my face. Okay. What we call an instantaneous velocity is the velocity at any 1 second in time. Imagine you're driving in your car, and you're not on cruise control. Okay, so take cruise control out of the options. How fast were you driving? Well, it kind of really depends on how steady your foot is. Does that make sense? Because you might have been going 50, you might have been going 52, you might have been, oh shoot, there's a school zone, drop it down to 30, right? Like, at any given moment in time, your speed might be changing. Does that make sense? So how we calculate an instantaneous velocity on this graph when you cannot calculate a slope is you use what's called a tangent line. Okay. Now a tangent line is whenever you have some sort of curve, and what you do is if this is the location that you want to find your tangent or your speed for, you draw a line that looks basically like this, where it's kind of equal on both sides around it, and it barely grazes the axis. That's called a tangent. Okay. If you learned about this in like grade 9 math, this is called a chord. It goes right through a circle. But if you have a circle right here and you have a line that just barely touches that, that's called a tangent. And so if you are looking for an instantaneous speed, which is a speed at any one moment on a curvy graph, one that goes like up and down and all curvy like, you have to draw in basically a triangle. Draw that triangle, find the slope of the triangle you just drew. Okay, so it's actually not all that hard. It's like with all graphing, it's a pain in the butt to do by hand. When I give you technology to do it, it's so much easier, obviously. Right? So let's try this example here. This is a position time graph. Okay, so position is really distance, and time is time. What does the slope of this graph represent? Velocity. Yeah. Okay. But is the velocity constant? No, because it's not a straight line. What that must mean is that this thing was slowing down. Everybody good with that? This thing is slowing down. And so if I want to calculate the velocity was always changing, but I can still do it. I just have to draw what's called a tangent. I'm going to make a triangle. Where's my shape tool here? I'm going to make a triangle as best I can so that I make a line. Oh, goodness, that's backwards. They all go that way? Oh, you're stupid pen tool. Can I flip it? Yeah, there we go. Okay. Sorry, I just need to build some triangles here. There you go. This is slightly easier for me because I have triangle building tools, but you can do the same thing by hand if you want. Just bear with me. Okay. Can you guys see how that is not a tangent? It's not a tangent because it kind of goes through the line there. So I'm going to take this, I'm going to kind of tilt it a little bit, and now I've made a tangent. The only downside is my stupid triangle is now off kilter. So this may not work as well as I'd like to, but if you kind of redo this, it looks like this came to about here and to about there. Can I just maybe redraw my triangle better now? Just find your rise over run. Now, there is no perfect way of doing this. It looks like my run is about 1.9, I'd say, because I was shy of 2. So I'm going to go with 1.9, maybe 1.8. And it looks like my rise was from about 25 down to maybe 2.5. So let's call that like maybe 22.5. Again, I'm doing my best because it's not perfect, but that would mean that at this location, my velocity is whatever 22.5 divided by 1.8 is. And I'm not going to bother finding that. If that's okay, I'll just leave that to you guys to solve for, because I don't really care what the number is. Just that's how you do it, right? But is your velocity the same at all locations here? Well, no. Let's put a triangle at this dot right here. Again, with where it's at right now, that is not a tangent. So, I mean, I got to manipulate this a little bit here. There, that's not bad for a tangent, but I'll have to redraw it as a triangle since my triangle tool sucks. So it looks like I'm going from about here to about here is where that triangle goes from. Oh, let's use a new color. Hang on. Let's color code this for you guys. Okay, there we go. So estimating, this is about what, like say 1.2 to 2.8. So can I call that 1.6 maybe? And then from here, it looks like I'm going from about 17 up till 30. So let's call that 13, give or take. So this location, my velocity would be 13 over 1.6. You guys feel like you could repeat this process a few times? That's how you calculate instantaneous velocity. It's not nice, it's not ideal, but you ultimately make a triangle out of it. So let me draw the triangle nicely here. Here's your triangle. The hypotenuse of the triangle is a tangent. And you find a rise over run for it. So I found this tangent right here. Rise over run is about my velocity. I'm going to change my mind. Let's find these velocities real quick. 22.5 over 1.8 is about 12.5. And 13 divided by 1.6 drops this down to 8.1, let's call it. Do the numbers make sense relationally to each other? Yeah, because they went down, right? Like, didn't we make a prediction before we started that our velocities were going to change? They were going to decrease. Based on this, we could actually now calculate the acceleration. Because what's the formula for acceleration? Well, acceleration is your change in velocity over your change in time. So my velocity changed from 12.5 to 8.1. Now again, I'm not sure that I can guarantee all these numbers. I'm really roughing it now. So can I just say my velocity is about 4? I think my velocity dropped by 4. And the amount of time that happened was from the 1 second mark to the 2 second mark, so in 1 second. So I think my acceleration is about negative 4 meters per second squared. That's how I did that. I found 2 consecutive velocity points by finding their instantaneous velocities by drawing triangles out of it. Again, I can't be accurate. And because I can't be accurate, I can't be that precise. So we do the best we can. And I think I found about 12.5, about 8. Let's call it 12 and 8. They separated by about 4. The difference in the time from when I calculated red to purple was 1 second. So 4 over 1 gave me negative 4 meters per second squared. About. You guys can see how computers made a huge difference in terms of physics, hey? Like, that's how we got to the moon. But have a computer that can run all these numbers for you? Awesome. So, good. How's that? Topic 3 for the day on the board there. Do you feel like you understand how to calculate the slope of a graph, which was not linear? You draw what's called a tangent, which is effectively a triangle that does not go through the graph. It barely grazes the side in the middle. Right? That. Skip this one here. I think we're good. Let's go to this part right here. Let's go to the last topic here. There is actually one more property of graphs that's useful. It's called area under a curve. Is the phrase we use. You know how we talked about slope being rise over run? Slope rise of the graph. And so if you take your y variable and x variable, y divided by x, to find the slope. So there's one more possibility. What if you take x and you multiply by y? Well, x and y being multiplied by each other is kind of like taking a length. So there are some scenarios where if you made a box out of this, and you found the area of this as a box, what you're really doing is you're taking velocity and you're multiplying it by time. Is there a formula that we can rearrange to make numbers divide by each other? There are many formulas, like say A equals B over C, or divide by C squared. Another one, B equals B over C, divide by C. We also use A equals F squared, divide. Are any of you familiar with this formula from last week? Like sometimes in physics formulas you divide. There are many formulas where you multiply. This is really clever, but take this formula right here. If you were to rearrange this formula and make it be velocity multiplied by time, you'd have found distance. Well, what does that mean right here? Take your x and y axes and don't divide them by two. Multiply them by two. Because velocity multiplied by time is distance. So if I found the area of this shape right here, it would tell me how far I traveled. So since we traveled a velocity of 2.2 in a time of 10 seconds, apparently we've traveled 22 meters, I guess. Clever? Actually, there's two things you can do with graphs. If you have graph data and you divide a rise by a run, find the slope. If that slope is equal to some sort of formula, you've now found a way to find yourself the sorry, no, that was for if you divide those. But there's a method multiply by each other, then that would work as well. I want to give you a scenario where this might be helpful. You guys know the formula D equals VIT plus 1/2 AT squared. Let's suggest nothing so that we can just blot that out. Do you see how these things are being multiplied by each other? What if I were to plot a graph of 1/2 A and T squared? Well, 1/2 A divided by T squared, that's not helpful. But 1/2 of A multiplied by T squared, well, that's now equal to T. So if I keep the graph 1/2 A by T squared, if I ask to find the area of it, that would then be. Now what's cool about this is that works for like a nice rectangle. Where you see how this graph kind of goes up and down and over and side by side, right? Now we can find by using some really cool things. You can find area, right? You spend a whole bunch of time going back to this, and then you spend some time. But I'm pretty sure if I were to compare the area of this graph right here, the area above the graph right here. So ultimately, if I were to ask you where you started, I think you're actually behind. Right? And the reason why is that velocity. So this is the amount of displacement you went that way. This is the amount of displacement you went that way. You actually went further backwards than you went forwards, basically. One last example, then we're calling her quits. This should be our last example here. Yeah. So this is the van that we're talking about, and it's the velocity time graph. If it's the velocity and divided by time, you get accelerated. That is. Okay, that's fine. Oh, what if I don't want to know that? What if I want to know how far you went? This graph tells you your speed. Well, do something different. Velocity divided by distance divided by time. Velocity. So if you kind of rearrange it and distance velocity time, then what you're really looking for is so I'm going to make a couple of shapes out of this. I'm going to make a triangle and a rectangle here. I'm going to make a really big square and then another triangle. I'm going to break it up into like some geometric shapes where this will be shape 1, that'll be shape 2, that'll be shape 3, that'll be shape 4. Find the collective area of all of those shapes. I know how far it went. As long as you know, like, paint, but like, daughter's for shapes. As long as you know your shape formulas. 5 to 30 is 25. And if it goes as high as 30, so 5 to 30 is. 30 to 45 is 15. The height is 30, but it's the triangle, so we got it by 2. This one right here is 20 by 5. And this one up here looks like 10 by 5 divided by 2. Find this area, find this area, find this area, find this area, add the whole thing. And what have you found? Area is. What's it called? Is that awesome? I want to teach one of my favorites. Show you like this is what science really is. I'll go to the look at me here. This helps teach you what science really should involve at its core, right? Like I said, I'm going to give you a worksheet tomorrow, and there's value in the worksheet, right? You need practice, right? But you need practice on like rearranging some math formulas, getting used to the formula sheet. If you take physics as a full semester, it's familiarity. Coach makes you shoot free throws over and over again, or Scott makes you do guitar chords or whatever, right? Like, so you need practice. But the better practice after that is we're going to do a lab on Monday. So I'll describe the lab to you. We're going to go and haul it. Hot wheels down the track. We are going to record distance down. Time it takes. We're going to have a right now. You guys record time. We're going to go like stop. You're all going to have a different answer. We're going to have to figure out, well, what is the round it to? Do we say that it's 22.5, 22.51, 22.57? We're going to have to talk about where do we just round. We're not going to just do a 1, like 5 data points. Will the data points be the exact same as each other? Probably not. So then we're going to graph it. We're going to look for outliers and then use a graph. And then after that, we'll actually talk about energy. I haven't even touched energy yet. But like these are the background. So, does that make sense? Cool. Thanks so much, guys. You guys were awesome. I hope you're nodding like yeah. So here's my challenge for you. Then we'll do this one more. 5 practice questions at the end of the lesson. Tell me what you know. Sound good? So you got about 10 minutes left to tell the bell. You probably can do both of those. And if you have